Take your attendance first. Okay, class. So let's start our lesson today. Okay, before I start, do you have any questions? No questions, eh? Okay. So we go back to A2 again. We go back to A2. You continue to discuss your AS paper, and we discuss back on next week, Wednesday. Okay. So we go back to A2. We go to the gravitation again. Okay. So I think we are almost done with this topic. So today going to be the last class. We're going to focus to this topic. Okay. So we're done with the gravitational field. We're done with the introduction of what Newton said about gravity, gmm or r squared. And we talk about the gravitational field strength, gm or r squared. Then field pattern, yeah, gravity, then g squared, and orbital speed of the satellite. And finally, we end up halfway discussing gravitational potential energy. This seven. Okay. So potential energy. We talk about potential energy. I think we haven't talked about gravitational potential yet. Two different things. Okay, so let's explore this today. Okay. After that is done with the topic. Then we could talk about xk speed. Okay. Okay, so we go to the slide now. So gravitational potential energy. I told you that there is a new definition. Not to say new, the original definition of gravitational potential energy has been, I told you last class. So this is the work done. So this is the gravitational potential energy definition. Recall back again. So gravitational potential energy at any point, at a one particular point, is actually the work done on the mass to move from infinity to that point. This is the gravitational potential energy at that point. Okay. So at infinite, the gravitational potential energy is 0. Okay. Right. At infinity, the gravitational potential energy is stated to be 0. When you go lower points, come to the surface of the Earth, your gravitational potential energy is negative. Okay. So technically, the value, you have a greatest gravitational potential energy at infinite, and it will be 0. And the formula for gravitational potential energy is negative gmm over r. Okay. It's negative. 3 reasons. Because it caused by an attractive force. At infinite, the potential energy is maximum, which is 0. Therefore, lower points must have negative values. Okay, the details will be the next slide. Why it's negative. Okay, so this is the movement. Doesn't matter. Okay, now we're going to talk about another quantity, gravitational potential. Earlier we talked about what? Gravitational potential energy. Now we're going to talk about, now we're going to talk about gravitational potential. Two different things. Okay. Like, you know, you go recall back your electricity. You got electrical energy, you have electric potential. Do you remember you have electric potential in your AS? Okay, in AS you learn about electric potential. Okay, so now you're going to learn something called gravitational potential. Okay, defined the same way. Electric potential, what is the definition? What is electric potential? Electric potential is what? Voltage, right? Volt. How do you define electric potential? Volt. AS. You should know this better, huh? What is electric potential? Work done per unit charge, right? That's the definition of electric potential, right? Work done per unit charge. Okay. Let's say the volt is 5 volt. What do you understand? The amount of work done is 5 joule of work done to move per unit charge. Okay, from one point to another. That is electric potential. So gravitational potential similar to electric potential. Can anyone suggest what is gravitational potential will be? Gravitational potential, the sign is phi. We use phi, Greek sign phi is equals to what is gravitational potential at one particular point? Like electric potential in a circuit. If this is a circuit, okay, you have a load. Maybe let's say this is 10 volt. On your left is positive 10 volt. Here positive 10 volt, and here becomes 0 volt. So the potential drops. Okay, the potential drops across the circuit. For gravitational potential also from a planet at every point away up to infinite. Every point has its own gravitational potential, like electricity. Every point has its own electric potential. In space, every point has its own gravitational potential. What is gravitational potential defined as? Same as electric potential. Work done per unit mass. So this is gravitational potential. Work done per unit mass to bring a mass object from infinity to that point. Yeah. This is gravitational potential. Okay. Work done per unit mass. Okay, if I go to the slide, see the definition here. What is gravitational potential at one particular point P? Let's say this is point P. It's defined as the work done in bringing unit mass or work done per unit mass. It's work done per unit mass for every mass from infinity to that point. It's called gravitational potential. Okay, work done per unit mass. Okay, what is gravitational potential energy? Okay, these two quantities are quite similar. They are linked actually. Gravitational potential is work done per unit mass. Gravitational potential energy is what? Work done on the mass object, moving from infinity to that point. Gravitational potential energy is not work done for every mass. It's like work done, the total work done for that object. Okay. Gravitational potential is work done per unit mass or work done unit mass from infinity to that point. So work is gravitational potential energy divided by the mass. Gravitational potential energy, just now we know, is negative gmm over r, right? The gravitational potential energy we know is negative gmm over r divided by the test mass. Test mass will cancel. So you get gravitational potential, negative gm over r. Okay, the unit is joule per kilogram. Okay. Okay, now let me go to the whiteboard. Okay. Sorry. Okay. So gravitational potential energy U negative gmm over r joule. The unit is joule. Work done to bring a mass object, to bring an object from infinity to that point. Okay, gravitational potential energy, gravitational potential, this is GP. Gravitational potential is defined as is work done per unit mass. Formula is negative gm over r. Unit is joule per kg. Okay, gravitational potential. If this is the planet of the Earth, gravitational potential energy at infinite is 0 joule. The earlier quantity which is introduced. The gravitational potential at infinite also, gravitational potential at infinite also 0 joule per kilogram. 0 joule per kilogram. Okay. When get closer, the point A, point B, we know gravitational potential energy get negative, right? Let's say gravitational potential energy at A is, let's say, negative 100,000 joule, let's say. The gravitational potential energy at B, let's say, is negative 200,000 joule. Okay. So let's say the body brought closer to A and B, the body which experienced gravitational potential energy of negative 100,000 joule, let's say possess a mass of 100 kilogram. The body which was brought from infinity to A and B, which possess this energy, negative 100,000 joule, possess the same mass of 100 kilogram. So can you calculate what is gravitational potential at A? Gravitational potential at A is work done per unit mass. That means work done per unit mass to bring from infinity to that point. Work done is actually negative 100,000 joule. Work done is actually the gravitational potential energy. Divide by the mass is possessed 100. So the gravitational potential is cancel is negative. The gravitational potential is negative 1,000 joule per kilogram. So gravitational potential is the amount of work done for every mass, every 1 kilogram of mass, how much of work done. That's gravitational potential. For each mass, how much work has been done. Okay. Gravitational potential energy is the total work done to bring the body mass from infinite to that point. Okay, I need to be very clear with these two quantities. Any questions, guys? Gravitational potential and gravitational potential energy. Okay, let me discuss further, explain to you further. Okay. Okay. So let's see. How many of you understand this? So for Earth again, at point A, they said the gravitational potential at point A is negative 5,000 joule. Okay. At point A, gravitational potential is negative 5,000 joule per kilogram. Sorry, per kilogram. Okay, let's say two people, let's say, reach the point A. Okay, two people reach the point A. The first person, as his mass is around 80 kilogram. Another person, the second one, has a mass of 50 kilogram. Let's say. Okay, so they are both at position of A. They're both at A. Okay. So now, what is the gravitational potential energy possessed by the 1 and 2? Gravitational potential energy possessed by 1 is what? So, gravitational potential given. Okay. So, gravitational potential energy is actually the mass of the person multiplied by the gravitational potential at that point. The gravitational potential at that point multiplied by the mass possessed by the person is the gravitational potential energy it has. So in this case, the first person mass is 80 kg and the gravitational potential at A is negative 5,000. Yeah, so this is the energy possessed there. Okay, 1, 2, 3, 4. So 40, right? 40, yeah, 40. It's a 400 negative 400,000 joule of potential energy possessed by A. Okay. So that's how you find gravitational potential energy from gravitational potential. How about number 2, the second person? Of course, easy, the same way, right? Is mass of the second person multiplied by the gravitational potential at that point will give you the potential energy possessed by 2. Okay. So this is how you find gravitational potential energy from gravitational potential. Okay. Okay, let me ask you one question. Those who listened to me just now about 15 minutes of lesson, let's see how many of you understand the concept I trying to want you to understand. Okay, let me check. Okay, now we are at the surface of the earth. All of you at the surface of the earth. We are having class at the equator. Okay. Okay, now maybe of course our mass is different. Okay. Maybe 2 of you in your class, 1 and 2. One has a greater mass. Mass of 1 is greater than the mass of 2. Okay. Now tell me, all of you have same gravitation, the 1 and 2 has the same gravitational potential energy or different gravitational potential energy? Do both of them have same gravitational potential or different gravitational potential? Okay, this is the question. Tell me, is it in between them, you put equal or inequality sign? If it's greater, which is greater? If it's equal, just tell equal. The 1 and 2, M1 greater than M2. Okay, both at the surface of the equator. U stands for gravitational potential energy, joule. Phi, this is your gravitational potential, work done per unit mass, joule per kilogram. So now tell me, the 1 and 2 have the same gravitational potential energy or different gravitational potential energy? Energy, same or different? Brendan, what do you think?
The gravitational potential energy of the first person is larger than the second person.
Very good. Gravitational potential?
They are the same.
They are the same. Yes. Good. So please remember. So all of us, if you are at the equator, all of us have same gravitational potential. Okay. But each individual have a different gravitational potential energy. Okay. Because gravitational potential, is it dependent by your mass? No. Gravitational potential is independent of your mass. It's only depend to the mass of the planet. Okay. Gravitational potential. Gravitational potential energy depend to your mass and also the mass of the planet. Okay, so how gravitational potential and gravitational potential energy is linked? This equation, gravitational potential is mass times gravitational potential. Okay, so those who got these inequalities and here equal, good, understand. Any questions before I proceed? No questions, Okay. So let me continue. Okay. So gravitational potential energy is negative gmm over r. Gravitational potential is negative gm over r. Okay. So U equals to the mass times the gravitational potential. Remember. Okay. Like for example, this is the Earth. At the surface, you know the gravitational potential. You know the mass of you. So you want to know gravitational potential energy. This is the formula to be used. Okay. Yeah. Okay, so our discussion based on this now. Gravitational potential is negative gmr. Okay. So now this slide tells change in gravitational potential energy. Okay. So you see this description. A satellite of mass m is lifted to an orbit of r from the center of the Earth. From the center of the Earth. Okay, from the center of the Earth. Okay, a satellite of mass m is lifted to an orbit r from the center of the Earth. So yeah, so the satellite was lifted up to a distance of small r from the center of the Earth. Okay, if the radius of the Earth is capital R, normally we use capital R for the radius of the Earth. Its mass is m. The Earth mass is capital M. Show that the change in gravitational potential energy is this. Show that the change in gravitational potential energy experienced by the satellite move from the surface of the Earth to that point of launching, launching. The gravitational potential energy it gained is this. Do you agree? Should be like this, right? The potential energy at the surface is negative gmm over r, right? R is the radius of the Earth. The gravitational potential energy at the orbit is negative gmm of small r from the center small r. So the changes is final gravitational potential energy minus initial gravitational potential energy. Negative gmm over r minus gmm over capital R. Get this. This is the changes in gravitational potential energy. This changes the gravitational potential energy. Okay. So any question from this arrangement?
So why is GPE negative again?
GPE is negative because in physics, if you have a positive potential means you are capable to leave the planet. You are capable to leave the planet without returning back. Then you have a positive potential energy. Okay. Let's say you jump. You will be pulled back to the Earth, right? You are entrapped. If you trap, then you have a negative potential energy. Okay, but in exam, if they ask why you have a negative gravitational potential energy, the answer you should say is in the few slides away. Okay, the B answer. The B answer. You see, just short while you see just part B. Why is the gravitational potential energy is negative? So this is the explanation. Since we have defined the maximum potential energy at mass at infinity is 0, all potential energy below must be negative. Please add another one. The potential energy caused by an attractive force. Okay, that's why negative. You need to add that too. Okay. So this is the answer. Like for example, yeah, correct. This is the answer. The gravitational potential at infinite is maximum, which is 0. And the potential caused by an attractive force, therefore, is negative. Who asked this question just now? Genuine.
Asked it, yes. Thank you, John.
Okay, you got the idea,
Yep.
Okay. All planets have a negative gravitational potential energy. As long as you are trapped, what I can understand, negative potential energy means you are trapped. Okay, you cannot come out from that, sticking with that planet. Okay, you are not free to move away anyway. You jump, you will get back again. Okay, you are trapped. So you have a negative potential energy. Okay, that means negative. Okay. Okay, we go back to the slide just temporarily. Okay. So, yeah. Okay, now let's explore. Okay, so this is the potential energy. This is the changes in potential energy. Last time, then what is MGH now? How MGH linked to this formula? From how MGH is formed? Okay, that's what we're going to discuss now. Okay, what links to MGH? Okay, actually the changes, this equation, MGH is actually equals to the changes in the potential energy. This is what do you call this equation. This equation has been about same as MGH. There's changes in potential energy. Actually, the MGH is calculating the changes in the potential energy, like in your AS. The changes in potential energy is MGH. Okay, but only works for a short distance. Only for a short distance. The height must be quite small, cannot be very far until go to the out of space. Then that's why I put this sign. It's not actually equal, it's about same. About same if h is far smaller than the radius of the earth. This is the condition. The h must be quite very small than the radius of the earth. Then we can say it's about same as mgh. Okay. Okay. Now 1 year past year, once they ask, I think 3 marks question, show this equals to mgh. In past year came out. Okay, how this equals to mgh? That's what we're going to do the next slide. How this become mgh? Okay, for this we go to the next slide. Okay, this is the next slide. Okay, so this is the derivation shows how finally it turned to become mgh. Okay, so to understand that, okay, we go to this picture first. Look at this first sign. The change. So now what we're going to do, we're going to bring an object from position A to B, which has an height of h. Okay, we're going to rise it for a height of h. Okay, so the change in gravitational potential energy close to the Earth's surface can be obtained by considering a 1 kilogram of mass placed at B, which is at height h close to the Earth's surface. Yeah. So first, we find the gravitational potential difference first. We find the gravitational potential difference first. Gravitational potential. Gravitational potential A to B. What is the change in gravitational potential? Okay, we are not calculating gravitational potential energy here. Gravitational potential first. Phi. Moving from A to B. So gravitational potential at B minus gravitational potential at A. Gravitational potential at B is what? Negative Gm over R plus H, correct? R plus H. Gravitational potential at A is what? Negative Gm over R. R. Okay. So now you see the arrangement here. We negative become plus, so become like this. Gm R. Okay. Then we take out the Gm, factorize it out. Gm. So it's 1 over R minus 1 over R plus H. Okay, so here after this, you see after this, this after from here to here, okay, we get the common denominator. So we times both, right? We times both. So R times R plus H at the bottom. So up on the left going to be R plus H. On the right, cross multiply, right? It's going to be R. Okay, this maths, right? I believe you know the step. We get the common denominator. Okay, then R and R on top might cancel, so it's tend to become like this. Okay. So this is what? This is actually what? This is gravitational potential. The changes in gravitational potential move from A to B. Okay, A to B. Okay, now. So the change in gravitational potential A to B, we got this formula. We got this formula already. The formula here and the formula up here is the same. Okay, is the same. Okay. Now, I told you 3 marks question, right? 3 marks question. This statement. This statement carries like 2 marks. Okay, this statement at the bottom. The statement is after you show gravitational potential like this, we give a statement. When h is far smaller than radius of the Earth, if h is far smaller than radius of the Earth, therefore the denominator, right? R plus H. The R plus H, right? R is so huge. Our Earth radius is 6,000 kilometers something. The height we rise maybe let's say 2 meter or let's say 1 kilometer. The R plus H is actually can written as R. Can take this R plus H as R because H is too small compared to R. So it become R squared. Okay, so the formula above turned to become GMH R squared. Okay, GMH R squared. This is the most important transformation. when h is far smaller than r plus h, we take it as r, so it's become r squared. The denominator become r squared instead of r plus h. Any question from here? You're almost there to get close to mgh. So the gravitational potential between A to B is gmh over r squared. Okay. But do you still remember gm over r squared is actually what? Gm over r squared. Gm over r squared is actually what? Is the gravitational field strength, small g. Gravity at the surface. So we change to gh. We change to gh. This is gravitational potential changes from A to B. Gravity is gravitational potential. Gravitational potential. Okay, now we want to find, therefore, change in gravitational potential energy from A to B is, how do you find gravitational potential energy? The gravitational potential, the differences in gravitational potential multiplied by the test mass. So gravitational potential change from A to B is GH, test mass is M, so you get MGH. So MGH is formed. Okay, this is how the link. Okay, so what is MGH actually? MGH is not gravitational potential energy at that point. It's actually calculating changes in the gravitational potential energy. You want to move from A to B. Okay, what is the change in gravitational potential energy? You can use MGH, but there is a caveat. The caveat is the H must be far smaller than the radius of the Earth. If you move, if the B location is another radius of the Earth, okay, or you move it up to out of space, like radius of the Earth is 6,000 kilometer, and you rise height of 6,000 kilometer from the Earth's surface, and you want to find what is the gain in potential energy, and use MGH. H you put 6,000 kilometer. It's not a correct answer. Okay, it's not correct answer because H have to be far smaller than the radius of the Earth. Then only MGH works. Okay, so in exam, as I said, 1 year they asked how MGH was formed. Okay, so you have to write this GMH over R bracket R plus H. You must give this statement: H far smaller than R plus H is R squared. This is like 1 mark. Therefore, it becomes GH. Then you can put MGH 1 mark. This equation is like 1 mark. Okay, so very important slide, linking between MGH with the new potential energy formula. Any questions? Try to understand the flow. The entire derivation, I think you remember this derivation, the changes in potential. Okay, changes in potential. Then H far smaller than R. You remember this the right hand side. The entire thing is enough, 3 marks. Okay, any questions, guys? So no questions. Okay, no questions. Let's try to strengthen the idea. We're going to strengthen the idea, gravitational potential and gravitational potential energy. Okay. Okay. So one question with solution. Try to understand the concept. Look at this diagram. A planet, blue color is a planet. Distance L away from the planet, there is a 2 point X and Y. Okay, X and Y is a distance of L away from the planet, and Z is 2L away from the planet. Double. Okay. So now here, so each of the concentric circle in the diagram represents the point that have the same potential. X and Y as the same distance away from the planet, so that's the same potential. While the Z lies on the larger circle 2L. Okay, now the gravitational potential at Y is negative 10 kilojoule per kilogram. What is that? The gravitational potential at Y. Gravitational potential means what? Gravitational potential, what's the formula? Gravitational potential is the phi. Is what is the formula? Negative Gm over R. What is the definition for gravitational potential? Work done per unit mass to bring from infinity to that point. For this case, for gravitational potential at y is negative 10 kilojoule per kilogram. So what do you understand by this negative 10 kilojoule per kilogram? That means to bring a unit kilogram of mass from infinity to that point y, 10,000 kilojoule of work need to be done. That's the understanding. Okay, 10 kilojoule per kilogram means what? 10 kilojoule of work need to be done to bring a 1 kilogram mass object from infinity to that point y. That's the work done. Okay, so A, what is the gravitational potential at x and y? If y is negative 10 kilojoule per kilogram, what is the gravitational potential at x and y? So gravitational potential at x must be same as gravitational potential at y, right? Because both are same L away from the planet, because the formula is negative Gm over R. The R for both of them, y and x same. So gravitational potential at x is also negative 10 kilojoule per kilogram. Correct? Any questions? Gravitational potential x is negative 10 kilojoule per kilogram. L, same, right? Okay, what is the gravitational potential at x? Z, 2L. Use this formula, negative Gm over R. When L is 10, when 2L is half of the gravitational potential at y, right? Because 2L, negative Gm over 2L. Negative Gm over L is negative 10. Negative Gm over 2L will be how much? It's negative 5, right? Half. Okay, that's the gravitational potential at Z. Any questions about part A? All of you understand the part A, gravitational potential. Okay, so I hope you understand gravitational potential. Z is half of gravitational potential at Y. Case 2L from the formula. Okay, B, I told you something to very commonly ask. Why is the gravitational potential energy is negative? So the reason is, please add one thing here. The first point you must tell is the potential energy is caused by an attractive force. It's caused by an attractive force. Okay, it caused by an attractive force. So this is one mark. Since at the potential energy at infinite is 0, 1 mark. Therefore, all must be negative. Okay. So you go to C now. Look at C. What is the change in potential energy of 1 kilogram mass when it's moved from Y to X? For 1 kilogram mass, small m, 1 kilogram, move from Y to X, what is the change in potential energy? So check what potential energy X to Y is final potential energy Ux minus initial potential energy Uy. But potential energy change is the test mass bracket potential at X minus potential at Y. So test mass is 1. Potential at X is negative 10. Potential at Y also negative 10. So becomes 0. So no change in gravitational potential energy. Because both are in the same gravitational potential. Okay, they are in the equipotential, we call it. Okay, same potential, no gain in gravitational potential. Okay, no loss or gain in potential energy. Okay. So next, Y to Z. If we move from Y to Z, so UZ minus UY. Okay. So M is potential at Z minus potential at Y. So you put the value is 5 kilojoule per kilogram. Okay. So this is a gain in potential energy. Okay. So Z to X. So potential energy at X minus potential energy Z. So you follow? It's negative kilojoule per negative 5 kilojoule. There is a mistake here in the unit. What is the mistake in the unit? Because this is a potential energy. It's all our potential energy. So should not be per kilogram. Just kilojoule only. Kilojoule. This change. Okay, any questions, guys, from here? Gravitational potential and gravitational potential energy. Okay, so hope you got the idea. Okay. So this is we skip this first. We go to the next one. Then we come back here. This concept is enough. Okay, the next part. We're going to talk about escape velocity. Okay. Okay, this is the last part of this topic. Escape velocity. Okay. What is escape velocity? Okay, this is a very interesting, what do you call very interesting fact. Escape velocity means the speed you need to possess so that you want to escape from the Earth attraction. That's called escape velocity or escape speed. Okay, like what? You are standing on the Earth's surface. Standing on the Earth's surface, you jump from the Earth's surface. What speed you need to jump so that you go to infinite and you are just free from Earth attraction? What is the speed required? This speed called escape speed or escape velocity. Okay, so we want to find what is the speed required so that you jump and you never return back to the Earth. So that's called gravitational escape velocity. Okay, the gravitational escape velocity is the minimum speed required for an object to escape completely from gravitational pull of a body and never fall back to its surface. Yeah. So how to find this escape speed? How do you escape from the Earth? You are trapped. Do you agree you are trapped on the Earth's surface because you have a negative gravitational potential energy, negative GMM over R. Your potential energy is negative. You are trapped. So you want to escape. Your kinetic energy must be equal to this potential energy, negative GMM over R. So that's what they do. You want to escape from the Earth's surface. Your kinetic energy must be at least same as the gravitational potential energy at the surface. Okay, but here negative has been removed because we just want to find the magnitude. We want to find the magnitude of the speed. That's why we removed negative. Okay, so at least should be equal to the potential energy. If you have more, it's fine. If you have more, after you reach the infinite, you still move forward. You have some kinetic energy. Okay, so the half mv squared is equals to gmm over r. This is escape speed formula. Root of 2 gm over r. Okay, escape speed formula. You want to escape from the Earth gravitational field? Okay, this is the speed you need to require. Okay, so check this formula. Do everyone, all of you, have same escape speed or a different escape speed to release from the Earth's surface? Same or different escape speed? Praveen, yeah.
Yes, sir.
What do you think?
Different.
Different escape speed. Why you say different?
Because of the difference in mass.
Yeah, so different mass. So escape speed, is it affected by your mass? No. It's just affected by which mass? Mass of the planet. Okay, the mass of the planet affects the. So all of us have the same escape speed. Okay, all of us have the same escape speed. Okay, so let's work out before we come to this part. Let's work out what is the speed required for our planet. Okay, they calculated for our planet. Okay, sorry, before that, I think I need to tell you this first. Okay, so root of 2 gm over r is the escape speed. Okay, but sometimes to calculate the escape speed, the mass of the planet not given. Sometimes the gm can be replaced with gr squared. Very important substitution. Okay, in question when you read, they're asking for escape speed, but mass of the planet not given. M not given, but they give gravity, the small g, the gravitational field strength given, radius given. Actually, the gm can be replaced with gr squared. How you know gm can be replaced with gr squared? Because gravitational field strength is what? Gm over r squared. Okay, so gm is gr squared. You can replace it. Gm can be replaced with gr squared. If they tell Earth, the Earth's surface gravity is 9.81. Sorry, it's 9.81, and they say radius of the Earth is r. Okay, so the gm can replace with the 9.81 times the radius of the Earth. Can replace. Okay, so the gm can replace gr squared. So you put gm as gr squared. R cancel. You get root of 2gr. Okay, this is what? This is your escape speed. So you have two formulas for escape speed. Root of 2 gm over r, but gm can be replaced as gr. So you want to escape from the Earth, the speed you require is root 2 gr. So we have calculated that what speed required to escape from the Earth is 2 times 9.81 times the radius of the Earth, 6.4 times 10 power 6 square root, is found to be 11.2 kilometer per second. This is the speed you need to jump. You want to escape from the Earth. Okay. Any questions, guys? Okay. So this is a very huge speed, you know. What is the height of Everest mountain? The Everest mountain, I think the Everest mountain height, I think is around 8,600, 8,600 kilometer. 8,600 kilometer. No, 8.6 kilometer, sorry. 8.6 kilometer, if I'm not mistaken. So you see, if you jump, just imagination, you want to escape from the Earth. When you jump with that speed, in 1 second, you already pass by the height of the Everest mountain by another 3 kilometer. That speed you need to jump in. You want to escape from the Earth. Okay. So, but this value is only correct without considering work done against the air resistance. Okay, without considering the work done against it. If the planet without air, yes, 11.2 is just nice for you to live. You go to infinite. When you come to the infinite, all your kinetic energy will convert to potential energy, and you will become to rest at infinite. So you won't move, but at the same time, you are not pulled back to the Earth anymore. Okay, this is escape speed. How do you get escape speed? Equating kinetic energy with the potential energy. Okay. Any questions, guys, about escape speed? Okay, no question. Okay, so now, why moon? By referring to the escape speed, why moon can't afford to have atmosphere? You know, moon don't have atmosphere. Why moon can't afford to have atmosphere? Referring to escape speed. Anybody have any suggestion? Why moon don't have atmosphere? Because moon don't have atmosphere, the air particle cannot stay at the surface of the moon. Okay, referring to the escape speed, what you can say? The moon has very low escape speed. Okay, the moon has a very low escape speed. So the speed of the particle easily can exceed the escape speed of the moon. Therefore, it can't have atmosphere. Okay, the escape speed of the moon is quite small. Because gravity of the moon is very small, so the escape speed of the moon is very small. The molecules, the air particles, easily can exceed the speed of the escape speed of the moon. So therefore, Moon unable to form a atmosphere. Okay, and same thing, Jupiter. Jupiter escape speed is far bigger than Earth because Jupiter has a more stronger gravity. Okay, so the Jupiter will possess is possessing a very dense atmosphere. Jupiter. Okay, so it seems the normal wind blow in Jupiter is like the speed of tornado, like the effect. It's like the tornado in our planet. Okay. Okay, so that's about escape speed. Okay, so after escape speed, we're done with the topic. Okay, so this all be done already. Okay, we already talked about satellite. So we go to the Word file. So after you learn about gravitational potential, energy, gravitational potential negative GMOR, potential energy is negative GMOR, escape velocity, root of 2 GMOR, 2 GR. Okay, done. That's it. Okay, these all are examples. So behind we have questions like an assignment. We spend one class to discuss this. You can give a try as homework. Okay, we have about 5 questions. Okay, use the formula you learn. Try to figure out these questions. Okay, we discuss the next class. Any questions, guys, so far? No questions? Okay, good. So tomorrow we'll be discussing these questions. Try to get your working. We share the working. Okay, we try to share the working. We discuss this one. Okay, I stop here. No questions. Okay, thanks.
Thanks, sir.
Thanks.